Hello, my name is Nathaniel Acosta, and this is Lab 4, Spring Oscillation. So to start, the purpose of this lab is to demonstrate oscillation and motion with the spring mass system. To model it, I'll use GoScript Simulation Tracker and graphing. Some physics principles that are present in this lab are Newton's second law, gravity principles, and the energy principle. And a quick preview of the results is that the predicted and observed model are very similar, but the observed model suffers from external factors, such as air friction energy loss compared to the predicted model. Start with the system and assumptions. The spring has a constant mass with negligible air friction. The point of attachment is stable and does not move. The spring starts some distance away from equilibrium to force oscillating motion, and the surroundings are the earth and the spring, and the system is the mass hanging down from the spring. This is part 1 of the tracker video, the unedited version of the observed oscillation. The mass starts at a positive angle from the horizontal, as you can see here at this point in the video, and it's let go, which results in a circular motion. This distance from the start of the video, right here, this attachment point to the spring, is 0.7 meters. This is part 2, the edited version of the tracker video with tracking the particle point mass of the mass. The blue stick is the calibration stick that is 0.7 meters long to allow for accurate data collection and results in this graph. The movement of the spring is presented as an oscillating function on the x and y coordinate graphs. The initial position of the mass right here is negative 0.04, negative 0.1450 meters, and the initial velocity of the mass is at rest at 0.00 meters per second. As you can see, I'll let the video play out, and it goes in a circular motion, and that results in this x and this y coordinate graph. Next up is a simulation. For the initial conditions of the simulation, the position is slightly below the origin, which is this blue line here on the graphs. Forces are gravity and the spring force, and a ball is used as the origin to keep track of the position of the mass that is connected to the spring. The final conditions is that the spring is to the right and below the origin, as you can see here from these final graphs. This is the x coordinate graph, this is the y coordinate graph. The forces are still just gravity and the spring force, and no energy was lost, as was shown by the change in energy versus time graph. On the right here is the formulas that was used to calculate each force. So the overall conclusion is that the predicted and actual position graphs are very similar, but the predicted motion has a much smoother curve due to not relying on human effort to track the motion, as well as ignoring factors such as air friction. As you can see, the y was a bit messed up due to human error. Some possible errors were once again human error. Due to the assumption that the density of the mass is uniform, and human error, the center mass may be offset from the points taken in tracker, and the simulation is slightly inaccurate due to not taking in external forces such as air friction or other such forces. So first, what does it mean? The energy principle is satisfied as long as there is no energy lost in the system due to any work, and all the energy is contained in the predicted simulation. In the observed experiment, however, there was some loss of energy due to friction, such as air friction, but it still upholds the overall energy principle, that no energy was lost in the total. What if the periods of oscillation is around 1.6 seconds for the x direction and 1.53 seconds for the y direction, and this difference in oscillation period is almost certainly due to effect of human error when measuring the position of the mass.